Now that we've looked at three-dimensional figures and we've looked at the area of a two-dimensional flat figure, we're going to put those two ideas together and talk about surface area of a three-dimensional figure. Surface area is the total area on the surfaces of a three-dimensional figure. One way you can see surface area is with some manipulatives that are often used in the classroom. This is a set of manipulatives that's sold by a company called NASCO. And you can see that there are clear plastic shapes, clear plastic three-dimensional shapes that have along with them some flat colored parts, and those flat colored parts are called nets. Now the nets are a representation of the outer surfaces of those three-dimensional shapes. So what we're going to be looking at when we look at surface area is the area of these outer surfaces. So if you can visualize the net, that may help you find the surface area of the figure. The other thing that you can think about is what would happen if you could just peel the outside surfaces off of the figure. What shape would you have and what area would they be? So let's start with thinking about right prisms. Now we know that a right prism has two polygonal bases. Those polygonal bases are parallel to each other. It has rectangular faces connecting up the polygonal bases. And we know that the name that's given to a prism is based on the shape of its base. So we could have a rectangular prism that has rectangular bases, a pentagonal prism that has pentagons for bases, a hexagonal prism would have hexagons for its bases. So let's take a look at an animation of what some of these prisms can look like and what the nets would look like for these prisms. So this is an animation from a website called learner.org. It's a website that was created by the Annenberg Foundation. And what you see on the left is a representation of a triangular prism that's rotating in front of us. And if you look on the right, there's an animation of the net of that triangular prism and what it would look like to peel that net off of the prism. Now we could also look at a rectangular prism. When its net is opened up, it has these two rectangular bases, so it will have two rectangles that are connected by four more rectangles. So we have 6 rectangles in all. A pentagonal prism will have 2 pentagonal bases, and they will be connected up with 5 rectangular faces. And an octagonal prism has 2 octagonal bases that are connected up with 8 rectangular faces. So if we're going to find the surface area of a prism, we need to know something about the dimensions of each of the faces of that prism. So let's take a look at this rectangular prism. We know that it has dimensions of 11 inches by 5 inches by 21 inches. So if you think about the rectangles that are forming the faces, we've got a rectangle on the left side that measures 5 inches by 11 inches. And in fact, we have an identical rectangle to that on the right side that we can't see. There's a rectangle on the top that has dimensions of 11 inches by 21 inches, and there's an identical rectangle to that on the bottom. And there's a rectangle on the front side that has dimensions of 5 inches by 21 inches, and an identical rectangle to that on the back side. So we can find the areas of each of these separate rectangles by multiplying their base times their height. So rectangle A has an area of 5 times 11, but remember there's a second rectangle on the right side that has an identical area, so we have two areas of 5 by 11, or 5 times 11. Same for rectangle B, that's the top, but the bottom's identical, so we have two of those same areas. And rectangle C, the front, is identical to the back, so we have two of those areas. And if we add all of those areas up, we have 782 square inches. Now if we look at the net for that, it would look something like this. Now some people find it easier to think of the net when trying to find the surface area of a figure. Some people think that that's just really confusing to look at. So you can be the judge of what's the best thing for you to look at when you're trying to find surface area. Now this is a prism as well. It's not rectangular. It does have two congruent bases. That's those kind of L-shaped pieces that are in the front and the back. And those are connected with rectangular faces. So what we're going to do is think about those different shapes that make up the flat surfaces. So the bases look like this. And if we want to find the area of this irregular figure, it might be useful to separate it into smaller rectangles, or we could decide what the area of that part that's kind of left out in the upper left corner is. But in either case, we need to come up with some dimensions for some of the other sides on this figure. We know that this top side measures 3 centimeters because it's the same length as the side that measures 3 centimeters in the original picture. And we know that this side must measure 2 centimeters because in all, the side that measures 2 and the side that measures 3 have to add up to the same 5 centimeters we see at the bottom. We know that this side measures 5 because it's parallel to a side that's measuring 5 centimeters in the picture. And we know that this side measures 3 because the vertical height of this figure is 8, and on the left side we have 5 inches of that, so this remaining vertical part would have to measure 3. So we could divide this up into smaller rectangles to find its area, or we could say, let's find the area of the large rectangle that's 8 by 5 and then subtract off the area of the piece that's kind of been cut out of it, that's 2 by 3. So the area of this shape is 34 square centimeters. Now remember, there's two shapes like this, one in the front and one in the back. So the total area of those two bases is 68 square centimeters. Now we'll just kind of hang on to that number for a minute, and we'll look at the other faces that we have on this figure. So let's just label them so that we know what we're talking about. There's a face that we'll call face A that measures 5 centimeters by 4 centimeters. There's one that we'll call face B. It's kind of like the top of a step that measures 2 by 4. There's another rectangular face. It's kind of like the front side of a step. We'll call that C, and it measures 3 by 4. There's kind of a top step to this that measures 3 by 4. Now there's two more faces that we can't see in the picture. One of them is kind of the back side of the figure, and it measures 8 by 4. And then there's a bottom that we're not seeing that measures 5 by 4. So that's the total area of all those rectangular faces. Now remember, we have to add to that the area of those two bases that we already found. So 104 plus 68 would be 172 square centimeters. So let's talk about pyramids and the surface area of right pyramids. Now what makes a right pyramid is that it has one polygonal base, and it has triangular faces that connect that base up to a vertex that's not in the base. So here's an example of a right square pyramid. You can see that the base is a square, And then there's a vertex that is not in that same plane of the base, but that vertex is connected up to the base by triangular faces. So let's look at an animation of some right pyramids and see what their nets would look like. So here's a triangular prism. It has a triangular base with triangles that connect that base up to a vertex. And you can see that all of its faces are triangles. A rectangular pyramid would have a rectangle for a base, and then all of its faces would be triangles that are connected up to that rectangle from a vertex that's not in the plane of the rectangle. A pentagonal pyramid has a pentagon for a base, and then it's connected up to that vertex with triangular faces. And a hexagonal pyramid has a hexagon for a base, and that base is connected up to that vertex, once again, with triangular faces. So when we're finding the surface area of a pyramid, we're going to have to find the area of the base, and then we'll have to add to that the areas of all the triangles that are connecting that base up to the vertex. Let's find the surface area of this right square pyramid. Now remember, it's got a square base, and then it has these 4 triangular faces. So we'll start with the base, which is a square that measures 4 centimeters by 4 centimeters. So its area is pretty easy to find. That would be 4 times 4, or 16 square centimeters. Now the triangular faces are triangles that have a base that measures 4 centimeters and a height that measures 8 centimeters. So we know that the area of a triangle is 1/2 times the base times the height, which would be 16 square centimeters. But that's just for one triangle. We have 4 identical triangles. So the total area of the 4 faces is 4 times that 16, or 64. Now we just need to add together the area of the base and the area of the 4 faces to get the total surface area, which is 80 square centimeters. Now right circular cylinders are a little more interesting, because when you look at the net of a right circular cylinder, what you're going to see is 2 circles that make up those 2 bases that are parallel to each other, and then if you can peel this cylinder open, you'll have a rectangular face that curves around those circles. So let's see if we can figure out where the dimensions of these shapes come from. Now this is a nice little animation from the learner.org website that shows you what happens if you peel this cylinder open. So let's play the animation. And you'll see that when we peel the cylinder open, we have a rectangle that has a length that is equal to the circumference of the circles that make up the bases. So when you think about how we find the area of a rectangle, it's length times width. So for that rectangle that makes up the side of the cylinder, its dimensions will be its length, which is the circumference of the circle, times its height, which is the height of the cylinder. If we can find that area and add it to the area of the 2 circles, we'll have the surface area of the cylinder. So let's take a look at how we're going to find a formula for finding surface area of a cylinder. We need the area of the 2 circles, and we know the area of a circle is pi r squared. We need the area of the rectangle, which is its height, times the circumference of the circle, which we know is 2 pi r. And that's how we get our surface area formula for a cylinder. Surface area is 2 pi r squared, because we have 2 circles, plus 2 pi r times h, 2 pi r being the circumference of the circle, h being the height of the cylinder. Let's find the surface area of this right circular cylinder. Now we know that in order to find the surface area, we're going to have to know something about the radius of the circle that makes up the bases of the cylinder, and we need to know the height of the cylinder. Remember, height is not necessarily a dimension that's going to look like it's up and down. Height is a dimension that connects up the two circles that are parallel to each other. So in this case, the height is 16. The 12 is not the radius. The 12 is the diameter. So the radius would have to be 6, half of that diameter. And that gives us a surface area of 2 pi times 6 squared plus 2 pi times a radius of 6 times a height of 16, which is 264 pi square inches. Now, just as before when we were working with area, we could substitute 3.14 for pi to get a decimal approximation for the area in terms of a rounded value for pi. But if we want the exact value, we would leave it as 264 pi square inches. Cones are also a little bit more interesting because they're made up of a shape that we expect, which is a circle. And then if you peel open the sides of a cone, you get a part of what looks like a part of a circle. It looks like a sector of a circle. So in order to find the surface area of this right circular cone, we're going to need to know the radius of the circle so that we can find its area, and then we also need to know what's called the slant height of the circle. That would be the distance from its vertex down the side to the circle's edge. Now the formula for surface area of a right circular cone is pi r squared, that's the area of the circle, plus pi r L. That's the area of the side of the cone, the part that looks like a sector of a circle. So R means radius, L means slant height. So to find the surface area of just the outside curved part of this cone, we are going to take pi times the radius of the circular base times the slant height L. So let's use that formula to find the surface area of this right circular cone. The radius is 5, and the 12 is not the slant height that we need. So we're going to have to work a little bit here to figure out the value for L. Now if you look carefully, you'll see a right triangle, and that right triangle can be used to find the slant height. So we know that in that right triangle we're seeing that the L that we're looking for is the hypotenuse of the right triangle, and the 5 and the 12 are the lengths of the legs. So we can use our Pythagorean theorem to find the value of L, which is 13. And we need that dimension, we need that slant height for our surface area formula. So now we have everything we need. The surface area is pi times the radius squared, so pi times 5 squared, plus pi times the radius, which is 5, times the slant height, which is 13. And we get an exact answer of 90 pi square centimeters. As usual, if we want a decimal approximation, we can substitute 3.14 for pi, and we can get a decimal approximation for our area. Now spheres have no flat surfaces. All of their surfaces are curved. And to find the surface area of a sphere, we only need to know one thing about the sphere, and that's its radius. The surface area of a sphere is 4 pi times the square of its radius. So, how do we find the surface area of this sphere? Well, its radius is 14 centimeters, so this is going to be pretty simple. The surface area is 4 pi times the radius squared. That would be 4 pi times 14 squared. Now remember, you have to square before you multiply. That's order of operations. And we end up with 784 pi square centimeters. And as usual, we could substitute 3.14 for the pi to get a decimal approximation. So let's put some of these ideas together for one last problem. Let's find the surface area of this figure. Now keep in mind, surface area means the area of the outside surfaces. So we've really got what looks like a cone that has half of a sphere on top of it. So we need to find the part of the cone that makes up just the outside of this figure and the part of the sphere that makes up the outside of this figure as well. The hemisphere is half a sphere. So if we take half of our surface area formula for a sphere, we'll have the surface area for that top part that's in green in this picture. So our radius is 4 centimeters, so 1/2 times 4 is 2 pi times the radius squared, which is 4 squared. So we have a surface area of just that hemisphere of 32 pi square centimeters. For the bottom part, we need the lateral surface of the cone. That means we need the part of the cone that's that curved part. And this is our surface area formula for a cone. But we don't need part of it. The part that says pi r squared is the surface area of the circle that's the base of the cone. And that circle is not in the surface of this figure, it's on the inside. So we don't need that part, but we do need the pi rl. That's the surface area of that curved surface around the outside of the cone. So pi rl in this case would mean pi times the radius, which we know is 4. We don't know the lateral height. So we're going to have to use Pythagorean theorem again. We know that L is our hypotenuse, so L squared equals 10 squared plus 4 squared. L squared is 116, so L is the square root of 116. It's kind of an awkward number, but it is what it is. So let's make our substitutions. The surface area of just that lateral surface of the cone is pi rl. So pi times the radius is 4. That's 4 pi times L, which is the square root of 116. So the surface area of just the outside of the cone is 4 pi times the square root of 116. So what's the total surface area? Well, we add those two things together. 32 pi plus 4 pi times the square root of 116 square centimeters. And we've got the total surface area of this figure. So that is the basics of surface area. We will try a few of these problems in class.